marathon to multiplication of like terms. And here it comes. We have the same 6 bracket 3 and 2 bracket 3, but this time around, instead of adding or subtracting, we are carrying out multiplication. See it here. So 6 trays times 2 trays. Let me, as before, get the same answer by using two different approaches. The first approach is the default approach. This is this first one. So 6 bracket 3 times 2 bracket 3 simply means let this be a single number, and let this be a single number, and let that single number multiply this single number. So 6 bracket 3 as a single number will give us 18. I hope you agree. And then 2 bracket 3 as a single number is 6. Therefore, this times this is the same thing as saying 18 times 6. If you multiply 18 by 6, the result is 108. So the answer is 108, a constant. Let me get the same 108 using a different approach. Now see the approach in this second line of operations. 6 bracket 3 times 2 bracket 3 simply means 6 times 3, see it here, then times, see times here, 2 times 3, see it here. So when expanded, this number operation has become this. By applying an association of numbers, that is applying associative law, we can isolate this 6 and 2 to be near each other like this, and let the two threes also stay near each other as they appear. Now, this has become this. The difference lies in the arrangement, but the result is the same thing. Multiplication obeys an associative law. So 6 times 2, then times 3 times 3. 3 times 3, when kept in index form, is 3 to the power 2. I hope you remember. Now, 6 times 2 is 12. Then times 3 to the power 2. See it here. That gives us 12 bracket 3 to the power 2. And if you evaluate 12 times 3 to the power 2, what you get is 108. How? This means 12 times 9. I hope you know why 9 is here. 3 to the power 2 does not mean 3 times 2. It means 3 times 3. And 3 times 3 is 9. So 12 times 9 is equal to 108. Please confirm that that is correct. This is entirely a different approach, but the same answer, 108, came to be. I want to isolate answers from among the answers we got after expanding 6 bracket 3 and 2 bracket 3 in this second line. We have this result, this result, this result, this result, and this result. We have 5 different results. I want to pick one out of the 5 results and then compare it with this first line of operation. I want to equate this to this because this is equal to this, or this is equal to this, or this is equal to this, or this is equal to this, even 108. I just want to write that 6 bracket 3 times 2 bracket 3 is equal to 12 bracket 3 to the power 2. And I compare it with this first one. Please let it happen. And here comes the comparison. 6 bracket 3 times 2 bracket 3 is equal to 108. See it here. The same 6 bracket 3 times 2 bracket 3 is equal to 12 bracket 3 to the power 2. So this is the answer, and this is also the answer. In pure arithmetic, that is, in addition, subtraction, multiplication, and division of pure constants, both this and this are possible answers to these two number operations. But if we do a corresponding multiplication of algebraic terms, both of them will not be possible. Only one becomes possible. Let me again replace this 3 by y and this 3 by y. Let us now check whether it is 108 or 12 bracket something that will be possible. Please watch out. And here it comes. Let this 6 remain where it is. Let this 3 become y. And from here, let y represent both 3 and any other number. The same thing happened here. To make 2 bracket 3 become 2y. Watch the way the answer was provided. 6 times 2 became 12. Then 3 times 3 became 3 to the power 2. Now that 3 is replaced by y, what it means is that this 3 here will be replaced by y. So 12 is still where it is, but this 3 is now y to the power 2. The bracket is now off, because if the bracket had been off in this first instance, this number would have been something different from what it is right now. I said earlier that it is good to separate constants from constants if one serves as the coefficient of the other. But if a constant is multiplying a variable, there is no need to put a bracket as it appears here. If I put a bracket here, no problem, but without it, still no problem. Because of simplicity, we choose not to put a bracket to separate this y to the power 2 from 12y. Therefore, 6y times 2y is equal to 12y to the power 2. Let us now derive a formula from this last statement. Notice that 12 was gotten by saying 6 times 2. And then y times y have been y to the power 2. The implication is that if it had been y times y times y, it should have been y to the power 3, depending on how many times the y appears when multiplying itself. Because it appears 2 times here, the power is 2. Therefore, let me use another line here to represent or to write the formula for multiplying like terms. Please watch out. And here the result comes. It says ay times by times any other thing y. The dots indicate that we can still have other numbers that possess y as their common variable. So we have that the answer is equal to ab dot dot then y to the power n. Let me explain this law in the light of this last statement we made here. I said earlier that this power 2 is not universal. It is 2 because y appears twice in this multiplication. So if it appears 3 times, this power will be 3. If it appears 4 times in the multiplication, the y will be equal to power 4. Because we don't know how many times a person will choose to multiply the y, let n represent any number of times that the y appears. This is exactly the n is here. If I had put 2 here, the implication is that the law applies to multiplying only 2 numbers of this kind. But because n is here, the message is that any number of times the y appears in the multiplication is appropriate for the situation at hand. Based on that, this y to the power 2 has become y to any power at all. What about this 12? Because we have 6 times 2 here, we have this 12. We could have other numbers multiplying the 6y and 2y. That means we have unlimited number of things that can multiply. Based on that, we have a times b, which is this 6 times 2 times anything else that can come afterwards. That is why these dots are here. But where did AB come from? Don't forget that this 6 is a constant. Here, A is a constant. 2 is also a constant. And here, B is a constant. So 6 times 2 corresponds to A times B. And A times B is the same thing as saying AB. So the dots show that other numbers can multiply with the AY and BY. I hope this law is now clear to you and you can use it when needed. All right, at this point in time, let us look at the division of like terms. And here it comes. This is division of like terms. 6 threes divided by 2 threes. The answer will be gotten in two ways, two different ways, but the answer turns out to be the same answer. 6 bracket 3 divided by 2 bracket 3 by default simply means let this as a single number be divided by this as a single number. As a single number, 6 bracket 3 is 18. As a single number, 2 bracket 3 is this 6. So when 18 is divided by 6, that is 18 over 6, the result is equal to 3. So by default, this is equal to this. Let us see a different method of getting the same 3 as the answer. 6 bracket 3 divided by 2 bracket 3 is the same thing as saying 6 times 3 over 2 times 3. Using law of association, we isolate 6 and 2 to become 6 over 2. And isolate 3 and 3 to become 3 over 3. So 6 times 3 over 2 times 3 has become 6 over 2 times 3 over 3. And when taken further, if this sign of multiplication is removed and both enclosed in brackets correctly, this expression has become this. That is 6 over 2 bracket 3 over 3. 3 over 3 is the same thing as 1 over 1, which is equal to 1. 1 times whatever is that whatever. So 6 over 2 is 3. 3 times 1 is equal to 3. 3 here, 3 here. With this default method, we have 3. With this alternative method, we still have 3. Our interest is in what happened in this line 2. That is alternative method of getting the answer to this number operation. Now, let me, like before, compare this default method with this alternative method. Now, see the comparison. This number operation gave us 3 as the answer. The summary is here. This number operation gave us all these answers, but I'm choosing this one. See it here. Now, with pure arithmetic, in which there is no variable, both this and this are possible. But when we begin to carry out this number operation of division with algebraic expressions, this first one becomes impossible since we don't know what that variable is. How? If I replace this 3 and this 3 by a variable such as y, in which that y can represent either 3 or just other numbers, will you categorically and surely say that the answer to this operation will be equal to 3? Certainly no, because you don't know whether 3 is what is going to be here or not, since y now represents 3 or other numbers. Instead, this second line is what is going to become possible. 6 bracket 3 divided by 2 bracket 3 is equal to 6 over 2 bracket 3 over 3, which means that we divide like term by like term in such a way that the constants involved divide and the variables, which are also the same power, divide. The constants are 6 and 2. See 2 dividing 6 here. The variable in this case is 3. That may turn to y afterwards. See it here, 3 over 3. Based on this second line, which we know works at all times, let me write a result of division involving algebraic expressions in line or in conformity with this structure. Let me do it. And this is that expression 6y divided by 2y is what we have here. 6 is still where it is, but this 3 is now replaced with y. The same thing is happening here. 2 is here, but this 3 is now replaced with this y. 6 over 2 is what gave us this 3. 3 over 3. Since each 3 is now y, we now have y over y. We can extend the answer to become 3, because when a number divides itself, as we saw earlier, the result is equal to 1. So 1 from here times 3 will still give us 3. Based on this, I want to write a law of dividing like terms. Please permit me to use this space here to do that. Now see it. It says AY divided by this BY is equal to A over B. Are you surprised? Again, look at this one. I have written 3 as the answer. Why is it that we are comfortable writing 3 as the answer? 3 is the answer because 6 and 2 are involved. If 2 other numbers are involved, the answer will still be a constant, but not 3. But one thing has become clear here. Whenever a like term divides a like term, the result is always a constant. Just see. Notice that in every like term, all the different constants or the same constants quantify the same variable in the same power. See, 6 is quantifying y and 2 is quantifying y. So y dividing y will still be equal to 1. Even if 6 is quantifying y to the power 2, for it to be like term with these 2y, 2 must also quantify 2y to the power 2. That the 2 may be 6y to the power 2 and 2y to the power 2. So that in the end, if what you have here is y to the power 2 over y to the power 2, the answer will still be 1 times this 3. And that is equal to 3. If you try it several times with different numbers, with the same pattern, you see that it is consistent. What it means is that whenever a like term divides a like term, we don't get a variable at the end. Instead, what we get is a constant. Therefore, A corresponding to 6, Y, the same Y is here, B corresponding to 2, Y again corresponding to this Y here. So in the end, this 3 was gotten by saying 6 over 2. Likewise, A and B will give us A over B, because in the end, what we get here is 1 when that variable divides the variable. So this is a law for division of like terms. Again, for emphasis, whenever a like term divides a like term, the answer will not involve or feature a variable. The answer will be equal to a constant. Now, before we take exercises, examples that will help us learn how to apply these laws, let us make some further observations on these laws. The two sets of numbers are used, 6 bracket 3 to 2 bracket 3, and then 6y to 2y appear to be like terms. But we have to know more about like terms just beyond what we have here. Notice that if this y is to the power 2 and this y is to the power 2, we will still call both of them like terms. So the message I want to pass here is that like terms are terms in which the constants available quantify the same thing in the same power. So far, it is power 1 we have been using all along. And this y is power 1, this y is power 1. So it means that all these laws are used, or these laws were derived with the belief that the powers of the unknown are 1. But that is not all-inclusive. It is possible for us to have power 2, power 3, power 4, and other higher powers of this unknown, as long as the two variables or more possess the same power. They are like terms. Based on that, in this first case, where we have a lot of adding and subtracting like terms, y is power 1, y is power 1. But the law remains valid even if y has other powers apart from this 1. Therefore, there is something I'm going to do to modify this law to kind of accommodate and account for, to make it account for other kinds of like terms which possess variables in other powers apart from 1. Now, Let n, small n, be any power of this y, provided that that power is here and is here. Because of that, I'm going to put that n here to make this flow all-encompassing. Please watch out. And here it comes. Ay to the power n plus or minus by to the power n, where this n can be any power, no longer just 1, but 1 is included, is equal to a plus or minus b y all to the power n. Again, ay times by times other things in y will give us this. Also, notice that this y has been power 1 all along. This n happens to be the number of appearances of this y as it takes part in multiplication of itself. What if there have been other powers of y before the y comes to multiply itself? Let it be that we'll have other powers apart from 1, like k. Let k be here as a power. If ay to power k and by to power k are multiplied, it means that like terms are multiplying themselves. At the end, if k is here and k is here, showing the former powers y had been possessing before multiplying themselves, then k must be here to be multiply this n, which has come to represent the number of times it appears in the process. Permit me to put k here, and k here to reflect the powers of y before the multiplication. Please watch out. And here it comes. This is ay to the power k times by to the power k. That k is here and k here. K is here. Makes them like terms. Before, k was 1. That is why n alone was here. But for other powers of k has appeared here. Therefore, the answer is AB y to the power kn. This last one remains valid. Whether the powers are more than 1 or 1, at the end, what we get after a like term divides like term remains a constant. Let us see some examples of number operations in algebra that exemplify the application of these laws of dividing, multiplying, subtracting, and adding like terms. Now, see some worked examples that will help us see how to apply these laws of carrying out arithmetic of like terms. First is 3x plus 5x. Which of these laws does this number operation conform to? It conforms to this first one. Our a is this 3. Our x is this y. Our power is this n. And the power for this x is 1. So our n is 1. And when the power is 1, we don't insist on writing it. We insist on writing the power if it is not equal to 1. If there is something up that is different from 1, we choose to write it. But if the power is 1, we choose to ignore it. The same thing applicable when 1 is a coefficient. We choose to ignore it and not write it. Not meaning it is not there, but it is simpler not written. So 3x means 3x to the power 1, and 5x means 5x to the power 1. So in this case, our n is 1 in each case. So that means that n, which is 1, still appears in the answer. So please, 3x plus 5x is equal to 8x. Which of these laws did I obey in carrying out this number operation? It is this first one I obeyed in doing that. I just added 3 to 5, the same way a and b are added here. And that is equal to 8. So 3 plus 5 is equal to 8. So, and then the variable stands juxtaposed. The answer becomes 8x to the power 1, which is 8x. Number 2 says 7g plus g plus 3g. This one exemplifies addition of like terms which are more than 2 in number. For instance, if I write this, it is not compulsory that the number of times you have to add like terms is just 2. Invariably, the dots we have in this second line are also here by principle. But just know it that this second example tells us that it is not just 2 numbers we have to add if they are like terms. 7g plus g, that is 7g plus 1g. 1 is its coefficient. It is not g that is called 1. Instead, 1 is here, telling us how many g's. Don't believe it when you are told that g is something as 1. G is not the same thing as 1. It means 1g. G is separate and 1 is separate. 1 tells us how many g's. The 2 are valid. So 7g plus 1g plus 3g. What do we do? The constants are to be added and then juxtaposed with that variable to the common power. What are the constants? They are 7, 1, and 3. So 7 plus 1 is 8. 8 plus 3 is 11. Then g to the power 1 is g to the power 1 here. So the answer is equal to 11g to the power 1, which is the same thing as 11g. Example number 3 says 9x to the power 2 minus 2x to the power 2. Which of these laws am I going to apply to simplify this number operation and give the answer? It is still this number 1, but this time around we are using this sign minus to carry out the number operation. So that means a minus b. That will correspond to 9 minus 2. 9 minus 2 is this 7 here, juxtaposed with the variable in the common power. Variable in the common power at this point, this time around the n is not 1, so it is going to appear in the end. It is 2. In the first case, the n was 1, so there was no point writing it. But now we have a need to write it because it is no longer equal to 1. So 9x to the power 2 minus 2x to the power 2 is equal to 7x to the power 2. I hope how this became this is clear to you, especially after comparing what happened here with what this first law is saying. The next example is this number 4. This is 12h to the power 3 plus h to the power 3 minus 5h to the power 3. Are they like terms? Surely. Why? These are 3 terms, and all the constants in the terms quantify the same thing. What are the constants? They are 12, 1, and minus 5. And what is the variable that they are quantifying? Is h to the power 3. What if what I have here is h to the power 2, and h to the power 1, or h to the power 4? That way, they will not be called like terms because the variables appear in different powers. But because they all have the same power 3, we regard the 3 terms as like terms. That means we can carry out subtraction and we can carry out addition of those terms. Let's go on, please. 12. So what we do is to carry out addition and subtraction where necessary, in the way this first law empowers us. So 12 plus 1 is 13. 13 minus 5 is equal to 8. And juxtaposed with h to the power 3. Therefore, the result is equal to 8h to the power 3. Number 5 example says 6m times 7m times 2m. Which of these laws do you think conforms to this? Which of these 2 laws do you think we're going to use to solve this problem or to get an answer to this number operation? Obviously, it is this one. 6m times 7m. What really happened is that we multiply the constants. The constants are 6, 7, and 2. 6 times 7 is 42. 42 times 2 is 84. Therefore, juxtaposed with the variable raised to power, number of times the thing appeared, this is power 1, power 1, power 1. That means our k is 1. Since it is 1, it means that this k will also be 1. And since it is 1, it means that what will be here is going to be 1 times whatever the power had been before. What will it be? In this case, it will be equal to power 1, power 1, power 1. And so we have power 3 because we have 6 times 7 times 2, 84. M times m times m is m to the power 3. So the answer to this number operation is equal to 84 m to the power 3. The last one, but not the least, is 20f to the power 2 divided by 4f to the power 2. Which of these laws are we going to make use of to simplify this number operation? It is this one. Don't forget that when a like term divides a like term, the answer is a constant. See it here. 20f divided by this 4f. 20f to the power 2 divided by 4f to the power 2. What happens is that this a is divided by b. Likewise, 20 is divided by 4. When 4 divides 20, the result is this 5. No variable will come at the end when a like term divides a like term. So the answer is equal to 5. Before you check if you've been following, find out if you can make sense out of the following statement that summarizes all these laws that we got out of arithmetic of like terms. And here comes a statement which we regard as a theory of arithmetic of like terms. This statement is made after we observe what we did to use these laws to carry out number operations in like terms. So this statement is like consistent observation made as we applied these laws. The law states, or the theory states, addition, subtraction, multiplication, and division of like terms simplify out. I just hope that to make sense out of this statement, it means that when we add, when we subtract, multiply, and divide like terms, we always get an answer. That is the meaning of the expression simplify out. At this point, time has come for you to test whether you have been following what I've been saying from the start of this section to this point. Please watch out for an exercise. And here comes the checkpoint. It says, using the laws, ay to the power n plus or minus by to the power n is equal to a plus or minus b y to the power n. Then a y to the power k times b y to the power k is equal to ab y to the power kn, and a y to the power n divided by b y to the power n is equal to a over b. Where you find appropriate, please simplify. 1, 7m plus 5m. 2, 5t squared plus t squared plus t squared. Number 3, 6h to the power 4x minus 2x h to the power 4. Please, are they still like terms? Use a lot of commutation and a lot of arithmetic of like terms to determine whether this is possible. Again, 6h to the power 4x minus 2x h to the power 4. Number 4, 8e minus 5e plus 11e. Number 5, q times 3q. Number 6, 3g squared times g squared times 2g squared. Number 7, 21x to the power 3 divided by 7x to the power 3. 8, that's number 8. The last one, that is 6xy over 9xy.